So we went through our Arrhenius acids and base definition and then switched it up to be more inclusive with the Bronsted-Lowry acid-base definitions and the conjugate pairs. And we talked about how water could actually be classified as both an acid and a base, that characteristic of amphoteric, being amphoteric. So since water can react as acid or a base, it can actually react with itself. And so we call this autoionization. So at any time, if you have a glass of water on your table right now, some of it is H2O, some of it is that hydronium ion, if you remember that one. And so hydronium ion, what we were talking about is really just H+. And some of it is a hydroxide anion. And so this autoionization of water results in there being this constant sort of flux or change between these different molecules. And so if we have water, it's going to autoionize into the hydrogen ion and the hydroxide ion. And so in these ones, there's going to be a constant composition where the hydrogen ion and the hydroxide anion actually each will equal each other. If you were to figure this out for perfectly neutral water, not acidic, not basic, perfect distilled water, the concentrations of both of those anions, anion and cation, would be 1.00 times 10 to the negative 7. It's a very small concentration because most of it is just water, right? So these ions would be dissolved in the water at this concentration, not molarity. So because these concentrations are constant, if you multiply them together, you also get a constant number. We call this the ion product constant or the dissociation constant, or lovingly the Kw, the constant of water, because constant totally starts with a K. And so the Kw could be defined mathematically as the ion product or the multiplication of those two concentrations by each other, or numerically as this value of 1.00 times 10 to the negative 14. Now, this value is amazing because all aqueous solutions adhere to that. So if one of these goes up, the other's going to go down, but their product would always remain the same. So it's this constant, because it starts with a K, right? Kw has a value, and it's also this really important organizing principle of all aqueous solutions. So it says it right here. So in any aqueous solution at 25 degrees, no matter what it contains, the hydrogen ions and the hydroxide ion concentrations should always multiply to give you this value, this 1.00 times 10 to the negative 14. It's a very small number, but it is always true. So I like seeing this as an equation, or you've done this before, as a bit of a triangle. So Kw is equal to the hydrogen ion times concentration times the hydroxide anion concentration. So putting into a triangle always allows you to solve for the missing one if you look at the relationship between the others. So Kw doesn't need to be solved for. We know that is always 1.00 times 10 to the negative 14. No units on that, just always is that. And then so these other two could switch. So calculate either the hydrogen ion or the hydroxide anion if we know one or the other. So this one says we know the concentration of hydroxide ion. So if we want to figure out the other one, I could take a look at the arrangement. The hydroxide anion concentration would equal Kw divided by my, whoops, other way around. Darn it. Did that backwards. Hopefully have a eraser handy. So if we're trying to solve for the other would be the hydrogen. And so that would be Kw divided by what we know. Sorry for confusing you on that. So I'm going to sub in what I know. Kw is always the same. So that would be 1.00 times 10 to the negative 14. And divide that by what we know is 1.0 times 10 to the negative 5. Remember, using your calculator, the EXP button is pretty critical. And so in this one, I would solve that my hydrogen ion concentration is 1.0 times 10 to the negative Now, concentration always has the units of moles per liter or molarity. So Kw, no units on that, but these concentrations, the other variables in this triangle that I've scribbled on the page here, do have concentration units or moles per liter. So I'll just try another one. I gotta erase my scribbly work there. So in this one, hopefully I'll do it right this time, we know my hydrogen ion concentration, so I'd be solving for my hydroxide concentration. It's always going to be Kw divided by what we know. So Kw is always 1.00 times 10 to the negative 14. And my hydrogen ion concentration is 0.024, or 25, sorry. So crunching the numbers on the calculator, I would get 4.0 times 10 to the negative 13 moles per liter. These ones I've also corrected for sig figs. In my given information there were 2, so my answer is going to have 2. So we've got a few more of these to try. I like using the triangle for them. One thing to take a note for also, in that I said when I was explaining Kw in the first place, a neutral solution, both of these were the same, 1.00 times 10 to the negative 7. Now, if we stray from being perfectly neutral, which is what acids and bases do, in an acid we'd have a higher number for hydrogen ion than hydroxide ion, and in a basic solution we'd have a higher number for the hydroxide ion. And so in these ones, if we have an imbalance, that's what's making an acid or a base. And so we're going to use numerical kind of analysis of these solutions to tell you if they are acid or base. So in these ones, we know one, we're looking for the other. And so it'd always be Kw divided by the one that you know. Kw is always 1.00 times 10 to the negative 14. Whoops. Always 4's turn into 9's with this drawing tablet. And then OH is 1.0 times 10 to the negative 7. So I get that hydrogen concentration is 1.0 times 10 to the negative 7 moles per liter. And again, to say whether it's neutral, acidic, or basic, we compare those two concentrations. So in this case, the two concentrations are the same. It's an equal concentration, which is how a neutral solution would be defined. So this would be a neutral, not acidic or basic. Let's do the next one over here. So this one, we know our hydroxide concentration again. So we're looking for the hydrogen concentration. That'd be Kw divided by what we know. Kw is always this 1.00 times 10 to the negative 14. True for any aqueous solution. This question, we know this concentration. I'm going to put this in my calculator. In this case, I'm correcting to 3 sig figs for a hydrogen ion concentration of, to check my math, 8.00 times 10 to the negative 12 moles per liter. So in this one, what I'm doing, and I'll just switch colors, I'm comparing these two numbers. This was my hydroxide ion concentration, and this was my hydrogen ion concentration. So which number is bigger? And this is where you have to remember that negative exponent makes for a very small number. So in this one, this would be basic, because it's actually a much higher concentration of the hydroxide ion in solution than the hydrogen ion in solution. So that's the way we're going to go through these, basically making that final call on if it's acid or base or neutral is kind of the add-on on this page. And again, we're always using Kw. So in this one, we know our hydrogen, so we'd be solving for hydroxide ion concentration. Kw divided by the hydrogen ion concentration, 1.00 times 10 to the negative 14, divided by the 10.0 moles per liter. This gives me my hydroxide ion concentration, and that works out to be 1.00 times 10 to the negative 15 moles per liter. Comparing these two to make the last claim, is it acidic or is it basic? Which number is bigger? Well, it's the hydrogen. So this would make it an acidic solution or an acid. Next one, carrots have a hydrogen ion concentration of 7.9 times 10 to the negative 6. I can't remember where that number came from. So we would solve for the other in order to say if carrots are acidic or basic. So that would be the equation. Kw, no thinking, it's a constant, times 10 to the negative 14. And I'd sub in what I know here. Do the division to solve for my hydroxide ion concentration, and I get 1.3 times 10 to the negative 9 moles per liter. So this always kind of does my head in. What I'm trying to do is compare these two numbers. So this number and this number, and which is bigger. So I have to remember that the smaller the exponent, the bigger the value. And so for carrots in this one, I would say that this number with the negative 6 is actually bigger than the negative 9. And so that makes carrots acids, so acidic. So the last ones, we'd want to do this calculation and make that final claim. I'll throw these answers up, and that's the end of this topic, using Kw as a definition of acids and bases in all aqueous solutions. So we've got our hydrogen ion concentration gradient is 2.5 moles per liter. So I'm solving for the other. Always Kw divided by what you know. And which is the bigger number, allows us to make that final claim. Eggs, whether they're acidic or basic, so making the final claim on this one would mean that they are basic or a base. The negative 7 is a bigger number than that negative 8.